Hello everyone, I am Federico Ticali. Some of you already knows me, as some of them know. So I am not anymore a student. I took my degree last month with this project, my thesis project. I'm presenting to you right now.
Federico, can you share your presentation on JFigures?
Yes. I thought I was already done. Non lo so usare completamente il Mac.
È difficile da...
Io non lo so che ha.
È strano. Che cazzo hai fatto? Solo macchina della mia vita tutto. Mannaggia, perché funziona male questo
Non lo so,
mouse?
non ho idea. Schermo, schermo. Finestra lascia aperta. E adesso? Cambia, per favore. Ok. Ti voglio bene.
Vai per questo.
Chi ce la fa? Non ce la fa. Ecco. Così blurrato, non capisco.
Can't share from Jitsi.
It's like it doesn't work, but I don't know why. It's like the mouse.
Just can you share your screen instead?
Yeah, I'm sharing the screen.
No, on Jitsi.
Yeah, I'm
Like
sharing.
share the full window.
I think it's what we are doing right now.
Attends, je sais pas.
Yes.
I think you should click on it. Yeah, now it's visible. Now it's okay.
Okay?
Yeah.
Sorry for the technical problems. Okay. My thesis took the name of collisional approach to measurement-induced space transition in open quantum systems. So I'm going to talk about what are measurement-induced space transition. Then I'm introducing my my study. It would be with this revision of more potential. The summary is this. I will give you an introduction of the problem and why what we are doing this. I'll give you fundamental concepts. I will talk about measurement-induced transition. I will develop my framework and my results, and then I conclude the talk. The introduction is this. The main topic, as already I told you, is measurement-induced transition. Why they are important? Because they allow to control the entanglement of a quantum system, of a chain of qubits, for example. And understanding how we can use it is fundamental to build the architecture in quantum technologies. So our aim in our study was to induce the space transition by means of environment measurements, because they are very widely studied in terms of closed system with projecting measurements on the system itself. So we wanted to develop a framework that allows us to induce this space transition by means of environment measurements, not only on the system. So enlarge the description using environments, adding an environment and measuring it inside the system. And then we focused on thermodynamics of the system, analyzing the inequality and introduction. So the sequence of the talk will be background, then I will talk about myths, and then I will give you the results. So the first ingredient is, of course, talking about a little bit about open quantum system. You are familiar, I guess, with open quantum systems, and you are familiar with the concept that the adding an environment in a quantum system is very it gives an impact on the description of the physics, because when we have a closed system, we know that the system is described by states, a cat that is cabin entirely the system, while in open quantum system this is not possible anymore, and we have to introduce a matrix rho, a density matrix, to describe it. And we have a limited knowledge of the system, while on the closed system we have a full knowledge of the system. When I tell you that we have full knowledge of the system, I mean that we have a global time map evolution, which is the Schrödinger equation. It's valid for every system, while when we have an open system, the time evolution map is not the same always, but it depends on how the environment is modeled. A popular way to model an environment is with the collisional approach. You are familiar with this, I guess. But the collisional approach is based on the assumption that the environment is made by small pieces called ancilla, and our system interacts at discrete time with every small piece of the environment time by time. So we say that it has a collision with an ancilla, and in the following step, the system has another collision with another ancilla, which is restarted. So every time, at every time step, we restart the state of the environment. And this is based on some assumptions like materiality and non-correlation and a big environment, because the fact that we restart every time the state of the environment, it's based on the fact that the environment is not touched by the interaction with the system, but the system, of course, yes, with the environment, with the interaction with the environment. And the collision map is this. It has some properties guaranteed by CPTP theorems. So it is a physical map in the sense that the density matrix set, the successive time step is a physical state. So we don't have to open out about this. As I already told you, we want to measure the environment. So we have to introduce measurement on the environment. So we are going to talk about the completely monitored conditional models, CM squared. Based on this framework, we have a system that interacts with the ancilla, and after that, immediately after the interaction, we measure the ancilla, and we have a tape of measurement of a quantity, a observable C. So, as we already know, measuring a system in quantum mechanics is not so trivial. We introduce a jump in the state of the system. So we projectively measure, when we projectively measure a quantum system, we have a nonlinear evolution like that. So the effect of measuring a quantum system is not so trivial. It is not so trivial even from a thermodynamic point of view. In fact, we are going to focus on reproduction that we are going to compute lately. The effect of measurement in quantum mechanics has an impact at fundamental level, even when we try to generalize the second law of thermodynamics. In fact, when we want to generalize the second law of thermodynamics in a quantum view, we have to distinguish two cases. One, the unconditional dynamics with no measurement, and we have a second law of thermodynamics very similar to the classical one. We have that the rate of the entropy production, unconditional, is greater or equal than zero. While when we have conditional dynamics, when we add measurements on our system, the second law of thermodynamics, this is derived in CM squared approach. We this paper highlighted the fact that in the conditional dynamics we have this kind of law, which is a little bit different. So the effect of measurement, as I already told you, is not so trivial, and they are connected with this relation where the variation is the variation of the convention at a single time step. So These were the ingredients, the main ingredients of our. So now I'm going to talk to you about measurement into space transition. They were widely studied in the past years as already covered in the view of closed system. So closed system with projecting measurement on them, and basically they studied the qubit chains basically. The idea is that we introduce a P measurement rate, and the idea is that we can reach a critical probability, critical measurement rate, which after that, with a P greater than this probability, this critical probability, we have a decent timing phase, in the sense that when we measure sufficiently fast our system, we don't allow the system to develop entanglement between its parts. So the idea is this. We are separating two phases. One, entanglement, when the system has the time to develop entanglement over time. So we are not measuring it sufficiently fast. And another phase, entanglement one, as I told you, with sufficiently fast measurement that don't allow the development of the entanglement between qubits in the system. Okay. For example, if we consider an qubit chain evolving by means of random unitary gates because they are high entangling, in this picture, we see that if we measure a qubit, we are destroying the entanglement with it, with the other component. For example, it interacted with the other qubits. So if we measure this, we break entanglement between this and this. So the problem is equivalent to a classical regression problem. If we want to evaluate whenever two subsystems of a chain, for example, are not entangled, are in this entangling phase. For example, in this study, they studied the entanglement between half chain of qubits and the other half chain of qubits, and they saw that there is a critical probability that separates two phases, a disentangling one and an entangling one. So, for example, with this simulation, we wanted to show you how this works. Now we can highlight this fact that the disentangling phase, we can separate disentangling phase to entangling using some entanglement measurement like S0 is zeroth entropy, which is not physically relevant, and S1 is the Riemann entropy, the physical relevant quantity. We see a similar pattern that we have. We plotted several length of chains of qubits we simulated, and for S0, for S1, we have a similar behavior, so that we have, in this case, with the low P, we have an entangling phase, and this can be seen by the fact that the entanglement is increasing in the side of the system, while from a point, from a critical probability, they found that in this case was 0.5. We have an overlap between all the curve, so the entanglement doesn't depend anymore on the sides of the system. And this I like the fact that we have a disentangling phase, so the entanglement is not increasing anymore with the size of the system.
Sorry.
And
this is the state of the system.
Yes, after a sufficiently long time, of course.
Is it a second order phase transition?
Yes.
So why don't you see here sharp discontinuities because
Because
of finite size?
you can see that, I guess, in the thermodynamic limit.
Okay, so it's like finite size.
Yeah, of course. Any other question? Okay. So now I'm going to show you our framework and our results. I'm going to remember you the aim. What is the aim? The aim is to induce this phase transition, adding an environment and measuring the environment. So we took inspiration on this kind of picture. So we consider a qubit chain interacting between neighbor pairs by the randoms, because we needed the only gates that they are eigentiming. We don't care about the specific coupling between the intrasystem coupling. And each qubit is coupled with an ancilla. So with the qubit, sorry. So an ancilla in our picture is a compound of n qubits, independent one from the other. And the coupling we choose for between the qubits of the system, the qubit of the environment, is a partial swap gate. Why this? Because the idea was that when we have a complete swap gate that is achieved when we have theta equal to pi half, the swap is complete. So we exactly swap the state of the qubit of the system and the state of the qubit of the ancilla. When we do this, and after that we measure we make a measurement on the state of the ancilla, we are going to simply measure the original state of the system. Of course, in our framework, we had to add some more, because we don't want we want to introduce this parameter p, which is a measurement rate. So our framework is like this: rho, which is initial state. We apply the partial swap. We ask with probability p if we should measure the state of the ancilla, for instance, and then we apply again the partial swap gate. Why this? Because of course, after the measurement on the ancilla, in order to affect the state of the system, we have to introduce some back action on the system. And the simplest one that allowed us to make our study was to apply again the partial swap. If you think about it, when we have a complete swap gate in this framework, we swap. Then we measure the state of the ancilla. We swap again. By means of measurement on the environment, we measured the system basically. So we expect that in this case we don't have any effect visible with the environment. So we expect to obtain exactly the same phase transition of the closed system I showed you before.
When you say you swap to theta, you unswap essentially.
Yeah. Yeah.
So when you're saying that when you're measuring, each qubit is interacting twice with the same ancilla.
Yes, once after before measurement and once after measurement, if the measurement occurs. Otherwise, we have to. It's basically to apply the partial swap with 2 theta.
Doesn't it defeat the whole purpose of the conditional model?
Sorry?
Doesn't this defeat the whole purpose of the conditional model? So the fact that you interact
No.
against
No, because the collisional approach is. Sorry, can you repeat the question?
No, it was just a curiosity that, right, in the
Can you repeat?
conditional model usually collide with the same.
Yes.
Theta ones.
Yes, I asked myself this question months ago, and the response is no. There's no problem, because you can interact you can model your collision how you want. Despite you don't have to, for example, make 2 ancilla to interact or adding correlation between ancilla. So if you isolate the system interaction with the ancilla, you don't have any problem. So I don't remember exactly the answer, but I'm pretty sure it's not a problem.
So as far as I understand it, you're saying I'm making a measurement probability P, and probability 1 minus P, I'm not making a measurement. That's it.
Yes. And of course, we are. I not said it, but I'm going to measure projectively on the environment on the computational basis. And now I'm showing you my results. So in this case, I had a thermal bath with temperature 0, so the state of the environment was 1, projective 1. We have made 20 realization, T equal 4m in this case. So when we fix theta equal to pi half, as I told you, we expect to obtain the same behavior as before. And I'm sorry for the bad quality, but it was very hard computationally speaking, so I had to do a few realization. In this case, as we see, the behavior of curves, there is not here a hierarchy. So the phase transition occurs because we don't have a hierarchy, so we are pretty sure that with with many realization, we have an overlap of the curves, so the visualization occurs and the results convince us. But even with that slightly difference in the coupling parameter theta, so this is pretty near to pi half, 1.5, we see that this absence of hierarchy is lost because we have here a hierarchy. In particular, we have that von Neumann entropy, it seems to be increasing with the size of the system. So in this case, we are pretty sure that the phase transition doesn't occur anymore. But and furthermore, I'm going to show you theta equal to pi over 4 because this is very interesting. That this is we have low entanglement even with low value of p in this case, with simply a partial slope gate that is maximally fixed in this case. So maybe there is more in this framework to highlight why, despite in the single in the closed system case, it was not possible this way, of course. So it is present due to the presence of the environment. So now, when I saw this months ago, I asked myself, but how I can be sure that this increasing entanglement is not due to the presence of the environment? Because in the initial case with the closed system, we evaluate the von Neumann entropy of half of chain, so that we are measuring the entanglement between half chain and the other half chain. When we add an environment, we don't have this anymore because we are adding an environment. So when we compute the von Neumann entropy of half state, we are measuring the entanglement between this half chain and the half chain of the system plus all the environment. So I asked to myself, is this a problem in this term?
So in this second case, in this case, you are basically you are looking at the partial state half chain of the whole system, not only of the but in your half part of the chain, you're also including the ancilla.
I have the complete state is the chain plus all the ancillas. Okay, so when we trace out all the ancilla and half of the chain, I remain with rho half, which is simply considering the alpha degrees of system of the chain of the system chain. And when I compute this quantity is a measurement of the entanglement between this part of the state and all the other part of the system plus the environment, because interacted with the environment and the system itself. I can't eliminate this effect.
So basically, you are not looking at the entanglement within the chain. You're looking at the entanglement.
I want to look at it, but I can't delete the parts of entanglement with the environment. So it's the part of this study to evaluate if this is a problem or not. But now I have an answer for this. So I asked to myself this, and in order to see if this correlation are increasing because the phase transition was not occurring anymore, I computed the mutual information between half chain and half chain, so that I'm deleting the correlation between the system with the environment. So I am evaluating the correlation between half chain and half chain. And we see that the hierarchy is achieved again. So we have an increasing mutual information with the size of the system. despite this large bug error. This was because we used this algorithm to compute the von Neumann entropy. So for higher chain, it's approximated because it was computationally very hard to get these results. But I'm pretty confident that this is the right behavior. So I can conclude that at 1.5, we don't have a phase transition anymore. So it's not a problem, it's not a matter of entanglement with the environment. And right now, I'm showing you the 2D plot of the von Neumann entropy in function of P and theta. And as we see, we have at theta pi half the behavior I showed before. So we have this entangling phase here after the critical probability. But it is interesting to notice that this shaded region is not a single point, but it seems to spread even with theta different from pi half in this neighborhood. So I'm pretty confident that the critical probability increase with when we go over the theta equal to pi half, and it goes to 1 pretty fast, but at least we can see that the phase transition occurs even with different coupling from theta equal to pi half, which is trivial, basically is the limit case. And it is even interesting to notice that we have two more shaded regions, one at pi over 4 and one at 3 pi over 4 with low P. This can be useful when for controlling, because with a simple tuning with the environment, we can control the entanglement even when we don't want to measure the entanglement. We want to measure the environment. It can be useful. And here I plotted the entropy reduction rate in function of theta and pi itself. And as we can see, it is oscillating with theta, with higher values or with theta equal to pi over 4 and 3 pi over 4. And it is increasing in P. And we have at theta equal to pi half, 0, exactly 0, but this does not surprise us, because as I already told you, in the case theta equal to pi half, it's like the environment is not present at all. So the effect of the environment, even thermodynamically, it cannot be visible. It's not visible. And okay, the last thing we did is looking at this. We wanted to, because it is very well known that when we have a phase transition, thermodynamic quantity like entropy or entropy reduction show, in this case, which is a second order phase transition, a discontinuity in the first derivative. So we wanted to see, plotting in this neighborhood, fixing P, if we can see enlarging the size of the qubit chain, if we can see discontinuity of this kind. And we wanted to see even if we can see this well, highlighting the fact that the phase transition occurs even when theta is different from pi half. And the results are
the biggest block is for how many qubits?
4.
So if you increase the number of qubits, maybe it's the black area becomes just a line. Because you were surprised that it was spreading.
I think so, because I have a plot in my thesis I didn't show you here with 6, and it is exactly the same. So I'm pretty confident that it is not a matter of size of the system, but it's a matter of coping, basically. And that way, modeling one challenge maybe can be to see what are the factors that contribute to this spread, to this I don't know how to say, to this range. Maybe we can control the range, how many large can be, but we don't know. Okay, it can be a future solve, future scene of this.
So one interpretation is that basically when you are using theta different from pi over 2, you can still say that you are measuring the system, but you are not collecting results of your measurements. Because you are entering the system with an environment which is equivalent to say that something is measuring, but you are not aware of the results, right? So what is this spread is most likely due to the fact that you are averaging many of your unknown results. So since you are not able to follow the actual results, this spread is due to this averaging over many realizations of your measurement apparatus. That's why you get this blurred part, which increases with theta. Probably one possible interpretation.
Okay.
Is not.
Thank you for the
Explanation.
Where was I was saying? So the last thing we did is that we fixed P, and I'm showing you two cases. One with P equal to 0.5, and one with P equal to 0.8. Because the aim was to see if this kind of how large when we have an IRP. Because when you have an IRP, you have a range of shaded region larger than before. So we wanted to see this. And as we can see, with the increasing values of the chain length, we have this value seems to get higher and narrowing. So we are confident that we are going to have a behavior like this in one unit. So we have the discontinuity we wanted to look for, and this baseline is basically what I told you before. So the range seems to be very short, but not a clear point. And it seems to enlarge when we enlarge the P, we fix up an IQ. And again, this is narrowing and getting higher with the size of the system. So we are pretty happy of these results. And the last thing I did is to plot the energy production in the conditional case, and the conditional case with n equal 4, to show you that the entropy is continuously produced with every theta, despite excluded theta equal to pi half. So when we are using this framework, we get every time steady state that is an informational steady state. So we are continuously getting information in the system and deleting information. So we are continuously producing entropy on producing entropy. So the conclusion, we managed to build a framework that is a presentation in the finite case. We managed to study the introduction for steady state elimination rates. We managed to find a singular point in the case theta equal pi half. And for the further looks on this, as you easily can see, the main problem of this study was the computational part. It was very hard. I used the tensor network approach to simulate these results. So, of course, I did on my laptop. So, computational improvement can be easily done. And as I already told you, in my point of view, the main interest should be to look for the deep reasons why we had this range and not a singular point. And how we can eventually control it, because it will be very interesting. And then I'm done. Thank you. Any other questions? Online? No. Okay.
So, uh, maybe this is a trivial, actually, a trivial thing. So you have looked at the entanglement between the chain, one half of the system and the other half of the system when you have the ancilla inside, considered inside as a function. So suppose that you look at the ancilla as if the ancilla is within the system itself.
Okay.
So does it make sense to look at the entanglement between these two sides of the whole system as you change the value of P? You see what I mean? So, but basically this is going, maybe it does make sense. So when saying, so you have looked at the basic framework is to look at the entanglement between the half chain and the other half chain.
Yes.
What I'm saying is also as to understand how things, to get an insight what is going on, to look at the entanglement between the left side of your system, where for left side I mean both qubits and ancillas.
You are suggesting to look at the entanglement between, for example, if you have a 8 qubits chain, 4 qubits coupled with
the
4
ancillas
ancilla,
and with the rest of the stuff.
Can be done.
As P is changed, whether you see any effect on the whole system. I mean, in principle, well, the map is actually you are getting information. You are making some measurement of the whole system already.
In this framework, yes.
Yeah.
I think it could be interesting to
Because
look at it.
this would fall within the standard, a sort of a subset of the standard measurement-induced transition, right? Because you are, but in a way you are saying whether the entanglement that you see in the system, where the change of entanglement you see in the system is due to the fact that you are actually transferring part of the entanglement in the ancilla, and maybe you are retaining part of this entanglement.
We can avoid this problem. Yeah.
And see whether this effect is due to, you can tell the difference. I mean, you can get insight about this effect you see.
It has to just, in my opinion. It's very nice. I will look at it. Thank you. Any other questions? Okay, thank you.